Personally, I think that graph theory came about quite naturally, and I think that it would have been invented, probably had been invented by many people at many different times. But the accepted canonical standard start of graph theory is usually attributed to the 1700s by a guy named Leonhard Euler. And today we're going to talk about Euler walk. So here's Euler. He lived in the 1700s, and most people, when they first see this, at least Americans, they say Euler. It's not Euler. It is going to be pronounced Euler. It's important to get that right. And he was born in 1707, died in 1783, perhaps one of the most prolific mathematicians maybe ever. He started what we now call graph theory with this problem, this sort of toy problem related to this town here. You can't see it so well there. This is a town called Konigsberg. The idea was that this town had these 4 different land masses and these 7 different bridges, and people had this game where they would try to walk, go on a walk and cover each bridge exactly once. So you can imagine trying to do something like this. Oh, I messed it up. I didn't actually get every bridge exactly once because I'm here and I want to use that bridge as the last one left. So I didn't quite make it. So that was the challenge. It's like, can you go around this town and hit every bridge exactly once? That's called the Bridges of Konigsberg problem. Euler heard about it and he wrote this little paper. And in that paper, he identified what is really the key issue here, which is, well, there's 2 aspects to it, right? One is that it doesn't matter that these are land masses and bridges, right? So the first thing he did was added a layer of abstraction. And graph theory is really all about having good abstractions for things involving connectivity. And so he introduced this idea that you just replace each of the land masses with a letter, and then a sequence of letters is valid if there's a bridge between those 2 letters, those 2 land masses. And so then you could think of pairs of letters as representing a bridge. And there you see immediately you have something very, very close to what we now call a graph. There is some difference that we'll see in a second. And so and he also identified that actually in this case, there is no way to walk across all 7 bridges of Konigsberg. And if you haven't seen that before, probably this is a simple enough problem. I would say pause the video and just see if you can figure out why there is no path. Because Euler figured it out, and I think any smart person thinking about it just a little bit will find this on their own. So we'll work that out. But now here it is in the abstract. And if we look at this graph, I've got the 4 land masses and the 7 bridges. You'll notice that it doesn't actually look like a graph as we've called a graph. So the first thing I want to do is I want to make it simple. Right, so we haven't used this word so much because all the graphs we've assumed are what are called simple graphs, which is that you can't have more than one edge between a pair, because if you think of this as, well, because it's a set, the edges is a set of edges, you can't have 2 elements repeated. So let's make it simple. Right, so a set doesn't include duplicates. So I'm just going to split this in half. Now this is already a big change because now I've somehow changed. It's like I put a little landmass in the middle of 2 of these bridges. I could actually split all the edges, and you have to convince yourself that if I can find a path on this graph with the edges split, that I could have found a path on the original set of bridges. Okay, and so here again is the question: can you take a walk which uses all the bridges exactly once? And again, it's all the bridges. So this really is often called the start of graph theory. It's also called the start of topology in some sense. And the key idea, the key insight that Euler brings here is this kind of abstract connectivity, right? That you take connected by a bridge and you represent it as a relation, right? It's just a pairwise relation, and then this symmetric pairwise relations, naturally lead us to graphs. All right. for the particular graph, like, can you walk across all 7 bridges covering each one exactly once? And the big answer is no. And if you've seen it before, or you stopped the video and worked it out, or you stopped the video and you struggled and you couldn't figure anything out, that's all right too. I'll show you why you can't do it. So the key is to look at the degrees of the vertices. Okay, so let V be an odd degree vertex. All right, so I've got some vertex. Let's just say, I don't know, let's make it degree like, here's V, and let's give it degree 5. All right, so now if I'm going on a walk here, so V is something, maybe it's like an island in the middle of the river here. As I come in, I leave again. All right, so here's one path. And then later I come back to it, because if I'm going to use one of these bridges, I come back to it. And let's say I come in this way and come out this way. Every time I enter and leave, I use up 2 of the edges. So the remaining edges, since I can only use edges once, the remaining edges stay odd, right? So if I think of it as actually deleting edges as I go, then entering and leaving an odd degree vertex leaves it with an odd degree. Similarly, if it had been even degree, it would stay even. But this also means that if I ever come back and use this last edge, I have to come in from the outside and I have to stay there. Which means that if I didn't start at this vertex, then I have to end at it. Okay, so if this walk that we're building enters and leaves V, then it uses 2 incident edges, and so it has to either be the start or the end of the walk. There's no way it could just be somewhere in the middle. And so we found that one of the ends has to be V. If it exists, right? If there is such a walk. So it starts or ends at V. Now, if you look though, if I go back, let's bring back my graph here. If you look at the degrees here, okay, the new ones that I added had degree 2, 5, 3, 3, and 3. So I actually all the vertices had odd degree, and I can't have more than one start and one end to a walk, and so there's no way to do it. This was kind of Euler's main idea, was to look at just the sequence of degrees. If that sequence contains either all even or just 2 odds, then you're good. Then, oh, actually, I should be careful about this. Okay, so I almost said the converse of what Euler proved. You see, what Euler proved is that if there are 1 or more than 2 odd degree vertices, then there cannot be a walk like this. Now, what's often attributed to him, but not actually in the original paper, is the converse of that statement, which is that if all the degrees are even, or if there's exactly 2 odd degree vertices, then you can find such a walk. And there's another caveat in here, which seems too obvious to state, but you have to state it, which is that the graph also has to be connected. Because obviously, if there's no way to get to some island, then there's no way, which has some bridges coming out of it, then there's no way to extend your walk there. Right? So it has to be connected, all degrees even, or exactly 2 odd degree vertices. That's the converse of what Euler proved. He states it, he kind of asserts it, but it was actually almost 100 years before someone actually proved that, and we'll see an algorithm for finding such a walk. It's not too hard, it's kind of intuitive, and I think he thought it was too obvious, but he didn't think this was too obvious to publish, so he probably could have included it. I'm sure he would have figured it out if you asked him. So the key was to look at the degrees, and if you have even degrees, you're good. You can continue the paths, and this is actually how a lot of algorithms will work. Will walk. The walking algorithms will work. So I'm going to take this though, and let's talk about it in terms of graph homomorphisms, because we talked about how a walk in a graph can be thought of as a homomorphism from a path into the graph, and so these Euler walks. These walks that use every edge exactly once can also be expressed that way in a very clean, natural way. I'll show you what I mean. So an Euler walk, when we talk about an Euler walk in a graph, right, this is, again, it's a homomorphism from the path into the graph. In this case, we want to use all the edges exactly once, right? So this walk as a homomorphism, if I look at what it does to edges, it's a bijection. So it has to be injective because it can't repeat an edge, and it has to be surjective because it has to use all of them. Okay, and similarly, if it's a closed Euler walk, remember a closed walk is like a homomorphism from a cycle into the graph. In this case, this is, again, it's a bijection on the edges. It's not going to be a bijection on the vertex set necessarily, unless the graph really was just a cycle or a path, right? You can repeat a vertex when you go around, but you can't repeat an edge, right? So just a reminder here, right, when we write these homomorphisms, because a graph is a pair of sets, the homomorphism is a pair of functions, right? One on the vertex set and one on the edge set, right? With this extra condition that the one on the edge set kind of comes from whatever happened to the vertices. All right, so now we can check that, let's just, a simple thing here, which is that whether or not you have an Euler Tor or not, this is a graph invariant. Now, we saw other invariants that looked at things like degrees. For example, the degree sequence of a graph, also known as sometimes called the score. If you sort the degrees, we know that that's a graph invariant. And so if you believe this claim in Euler's paper, and the one that I've made already, which is that as long as the degree sequence looks a certain way, then you know you have an Euler Tor. Or, I'm sorry, I put Tor in here, but of course this is a closed walk, right? Because if it's a bijection, then it's definitely injective, which means it's a Tor. This is why you might also see these called, this is sometimes called a Tor, Euler Tor, or an Euler trail, right? Because an injective walk is a trail, and if it's bijective, then it's injective. All right. So we kind of, if you just believe the thing about degree sequence, you would get that this is a graph invariant. But actually, we can prove directly that it's a graph invariant without anything fancy. Right? This actually follows really directly from the definition. So if we have two graphs that are isomorphic, so let's let F be an isomorphism between G and H, and let's say W, right, mapping our path of length M, right, M is the number of edges, into G, where this is an Euler Tor, or I guess this is an Euler walk. I put Tor here. I could make this a cycle if you like, either one. Right, this is an Euler Tor walk. So if I have this Euler walk, then this is going to start to look like so many of the proofs we've done. Like once you express the problem clearly in the right abstraction, in this case the abstraction of homomorphisms, like the answer becomes really simple to state, because I want to prove that if I have the Euler walk in one, then I have the Euler walk in the other. So I want to take the Euler walk and kind of push it through the homomorphism, and you just do that by composition, right? So this looks like almost exactly the same as the proofs we've done before. So here it is, F composed with W, right, which is now going to be like, it takes the path, right, into G, and then from G into H. So this is a walk, right? By definition, this is a walk in H, and it's an Euler walk because if I look at this function just on the edges, this has got to be bijective because it's the composition of two bijective functions, right? This is Fe composed with We, right? And since by definition this is an Euler walk, so We is bijective, and this is an isomorphism, so Fe is bijective, so their composition is bijective, and therefore this is an Euler walk. Okay, and that's it. So we showed that if the graphs are isomorphic and one of them has an Euler walk, then the other one does, and I can replace this with a Tor if you like, right? We could put this Cm, and this could be a Tor. And so if one of them has it, then the other one does, and vice versa, because if you have an isomorphism, I can do this the other way. And so I see that I have a nice graph invariant here. Okay, so thinking about expressing these Euler walks in terms of homomorphisms, is really good. And at first you might think, like I hear this a lot, that sometimes people say, you know, why go through this step of this extra abstraction, right? Like thinking about the walk as a homomorphism where it might seem just so simple to say, hey, I'm just going to talk about a sequence of vertices. Well, this is kind of the reason. And also, you know, in a way, we should take this story of Euler as some good reminder that sometimes having another good abstraction allows you to do all kinds of things more simply, clearly, and correctly. And so in this case, this is really a beautiful abstraction for talking about Euler walks. And I think this little sanity check here, again, it just demonstrates how you take an object or a structure that's in one graph and you push it through the isomorphism. In fact, you could have pushed it through another kind of graph homomorphism. If F here, you might want to check, like if F wasn't an isomorphism but was just a homomorphism, you know, you would still get a walk in H, but the walk wouldn't necessarily be bijective. And so you can kind of get, just by expressing some property of this function, you can understand it in terms of this Euler walk, which again has an intuitive definition, says, hey, you walked around, you used every edge, you didn't repeat an edge. But these properties of the functions inside the graph homomorphisms kind of encode a lot of the things that you would have to check anyway. Right? So we can skip all those steps because they're just in the definitions. All right. So so we kind of worked through this case of what is necessary to have an Euler walk, right? So the graph must have 0 or 2 odd degree vertices. Those are the only two cases to have an Euler walk. So that's necessary. But the fact that this can also be sufficient, or nearly so, is kind of is something we should check here. So the first one, I said this is this is obvious, I think, is that the graph really has to be connected. If it were not connected, let's do the Tor case. This is the easier one. An Euler Tor. In this case, it's just going to be all degrees even. And so why might this be okay? Like, why is it that if I have all degrees even, then I can necessarily find an Euler Tor? Let me give you an example where this kind of seems like it goes wrong. At least if I just want to be greedy about it, I could just start at a vertex, and if I go in and then out, right, so here's my walk. Let's label these A, B, C, D, E, F, right? So I'm building up my walk, and I go, okay, A to B to D, and as I remove these, I went through B. It had degree 4. Its remaining edges give me just degree 2, so it still has this property. And then I go, okay, I guess I only have one choice here. I go D to C. Now again, I've gone through D, and its result is degree 0. And now I get to C. If I go to A now, I can't extend this path anymore. I can't extend the walk to a bigger Tor, even though I have some extra edges here. So there were edges I didn't use, so just being like straightforwardly greedy is not such a good thing. On the other hand, I know that the remaining degrees, if I look at the edges that have not been used, and I take this sort of subgraph induced on those edges, I get still a graph with all even degrees. So now let me draw in a separate color. I could start from one of those vertices and try again to be greedy. And now I've covered all the edges, but I didn't have one Tor, or I didn't have one Tor, I had 2 Tors. And so instead of using this, I want to kind of swap these, right? I want to replace this Tor. What was the second Tor I had? I guess I went B, E, F, C, B. And then what I'll do is I'll just kind of splice that in, right? So I'll put that one in here. And so I'll go A to B to E to F to C to B to D to C to A, right? And so I get this loop-de-loop. I'll go around twice. But now I was able to kind of do a little surgery on my cycles and put them into one. So this idea goes back to, it's attributed to Heyerholzer, published in 1873, right? So we're talking about like 100 years later. And really the idea is, again, just a kind of greedy walk where you just kind of go in and out. You take any first edge you see, and then when you get stuck, you kind of splice in a cycle. And you can do this recursively. So you kind of go back and splice in a new cycle. I'll make this more explicit when we actually write some code. And because the graph is connected, right, this was important, because the graph is connected, you're always going to find that if there's any edges that you missed, they have to be connected to a vertex that you hit. And that way you can go to that vertex that has some remaining edges coming out of it, but that used some edges of the cycle you found, and then you extend it from there. We'll do that in code in the next video.